अस्सलाम वालेकुम फैसलाबाद। अस्सलाम वालेकुम फैसलाबाद।
अस्सलाम वालेकुम।
वालेकुम सलाम, क्या हाल है भाई? ठीक ठाक?
फर्स्ट क्लास, यूनिवर्सिटी ऑफ कराची।
जी जी, मैं गवर्नमेंट यूनिवर्सिटी से हूँ, रियाज अहमद।
ओके सर, थोड़ी आवाज़
आवाज़
सही
ठीक
करें अपनी।
आ रही है?
हाँ
मैं कह रहा हूँ मेरी आवाज़ और वीडियो वगैरह सब कुछ सही आ रहा है आपको?
हाँ, सही आ रहा है, सही आ रहा है सर।
अच्छा, ओके जी, बड़ी मेहरबानी।
आपको आवाज आ रही है?
जी सर।
ठीक है, ओके। मेरे ख्याल से अभी कोमल कनेक्टेड है
और
जी जी,
कराची
गवर्नमेंट
यूनिवर्सिटी
यूनिवर्सिटी कनेक्ट है।
और अपना इंट्रोडक्शन करा दें काइंडली प्लीज।
कराची यूनिवर्सिटी।
जी
हेलो।
जी
कराची
थैंक यू
यूनिवर्सिटी
कराची
है
यूनिवर्सिटी।
जी। और सेकंड पे है गोमल यूनिवर्सिटी भी कनेक्ट है सर।
ठीक है,
गोमल यूनिवर्सिटी।
जी जी, गवर्नमेंट यूनिवर्सिटी कनेक्ट है, रियाज अहमद।
अस्सलाम जी, कैसे मिजाज हैं रियाज आपके? हाउ आर यू?
अल्हम्दुलिल्लाह ठीक ठाक सर जी, आप ठीक ठाक हैं?
Becca, any question relevant to the previous two discussion? Because I think we are today getting into more of अच्छा जी। आपको कोई anything you'd like to discuss? से I think जहाँ पे भी ज्वाइन करेगा, चाहे पेरिफेरल साइट हो, anywhere which is, you see, because inhibitors or enzymes can interact to various places in protein. There are active sites and there are peripheral sites and a number of other things also. Wherever it is closely bound to the protein, and that closely bound is is a quantitative term. Uh, 6 angstrom or less, because you can only observe observable NOE. You can only observe NOE when the distance is either 6 angstrom or less. So it means that if you observe a greater signal enhancement, that means they are much more closer. So it's a quantitative relationship between the enhancement in signals due to NOE and the distance, right? और ये जरूरी नहीं है कि active site पे हो. You're very right. It can be anywhere, because remember, multiple proteins, catalytic proteins, have multiple sites. They can have multiple active sites also, and it's not necessary that that inhibitor only bound to the active site. It can only block the way of the physiological substrate. It can bind to the peripheral site and change the conformation, and it become inaccessible for the physiological substrate. A number of different ways of making a catalytic protein non-efficient, or so-called modulating. Thank you. Modulating the activity of catalytic proteins. Thank you. हाँ, दोनों एक साथ होंगे तभी you would be able to see relationship. This is one way of doing it. So if you have multiple of different types of molecules, the molecule which fits the best with the catalytic protein would give you the enhanced signals, and that's how you identify. इस तरह आप identify कर सकते हैं is a high throughput screening of inhibitors, and it's really very fascinating because it is more of a quantitative and mechanism based, right? Mechanism भी बदल जाता है, quantitative भी है nature में, इस तरह होता है. And there are lots of very interesting. We would have full 2 days of discussing the role of NMR spectroscopy in drug discovery and development, because I think now most of the development in the field of NMR spectroscopy is focusing on biological side, on biomedical side, on drug discovery, is moving beyond structural elucidation of small molecule. Application is numerous, and they are diversified. So there is a need of revisiting NMR spectroscopy with reference to other application than conventional application of elucidating the structure of small molecule. Okay. Any other question? See, the modern spectroscopic techniques are now very interestingly divided. Remember, the whole spectroscopy was dealt with the interaction of light with the matter. Now people are defining a spectroscopy on the impact on matter. For instance, some of them deals with the electrons, right? Some of them deals with the neutrons. Some of them deal with nuclei as a whole. Some of them deals with the molecular motion as a whole also. So if I give you the example of electron spectroscopy, X-ray is one example. If I give you the example of neutron spectroscopy, neutron diffraction is an example. if I give you the example of a molecular spectroscopy, IR and UV is an example, because the whole molecule behave. If I give you nuclear, so-called nuclear NMR spectroscopy, then NMR is an example also. So the nuclear spin as a whole, whether it contain a neutron or not, is flipped with reference to radio frequency. Radio frequency is the weakest end of the electromagnetic radiation. Anything else you'd like to know? Alaikum salam.
Sample which is neither the pure crystalline form nor in the pure amorphous form. I mean, the crystals are very smallest needle, like we want to form their better crystal to examine under the axis what are the methods. And it's directly related to the NMR. It's better to do.
Sure, I'll tell you how to crystallize samples.
I want to include one statement. Once Doctor told me that to make a crystal is not a science, it's an art. So there are several, so many ways of making crystals. It's just a hit and trial, and nobody knows at which will give you the good results.
Yes.
Until you don't try.
And there are lots of myths about crystallization. Friends, one of the most famous myth is that if you get a crystal in one lab, getting the crystal of the same compound in the same lab is greater than having crystal somewhere else. Because लोगों का ख्याल ये है कि there's some quantity of this crystal, it's always suspend indefinitely in the environment of that particular lab. So, but certainly crystallization is an art. There are a lot of automation because you need to try lots of combination. Therefore, there are robots available, crystallization robots available, which take nanogram quantities of sample, divide them in 10,000 different dilution, and then use 10,000 different types of combination of solvents. And then eventually, it all happen in multi-well plates, and then you have the camera fitted there. When you see a growth of a crystal, you would be able to observe from your own computer that in 8,997 well there is a crystal. You would be able to observe it. So different combinations of crystallization is certainly a science and arts, because there are lots of automation, there are lots of understanding of the crystal phenomena. See, I want to tell you something very interesting. Long time ago, nobody has done it, but I still believe that X-ray crystallography, you need to have a periodic arrangement of compounds. That's what you need to have. Remember when I was discussing X-ray during your courses, I said that the prerequisite of having a constructive interference and observable diffraction pattern is periodic arrangement of molecules, right? So if we can somehow create a periodic arrangement of a molecule without crystallization, you can get a diffraction pattern. I believe on this. I feel that nanopoles, cyclodextrins or other, which has holes in it at a periodic interval, and if your compound can eventually seep into these holes and arrange in a particular manner, this nano crystal of something different would become a crystal in which you have your compound periodically arranged exactly in the same manner as you would see in a crystal. And this should show crystallization also. This is my theory, right? I don't know, nobody has done it so far, but I believe that someday somebody would do it. Anyway, again, Assalamu alaikum wa rahmatullahi wa barakatuh, and I think we will start our discussion. I came here about 12 minutes before 2, and I wanted people to ask me a question. Not many questions were asked, but let's start. Last week, we discussed NMR spectroscopy in a holistic manner. And I told you that in order to take benefit of NMR spectroscopy, we need to understand the strength of NMR spectroscopy. So we had a detailed discussion of various spectroscopic techniques, their strength and weaknesses, what type of information they provide you. So we understand that this is the combination of different spectroscopic technique which gives you information about the structure of a molecule, and no single technique is capable of giving you all the information. Even if you have a structure from one single technique, for confirmation of the structure you need to have information from the other technique also, and that is the reason why I took you through all the way from purification of compound to the solubility, to the quantity of sample, which approach you would like to follow if you have less sample, which approach you would eventually follow if you have more samples, and I took you through the process of various spectroscopic analysis, UV, IR, NMR, mass spec, of various types, and the objective was that we start looking NMR as one of many techniques. Of course, a very important technique, but one of many techniques, because every technique provides a piece of information, and these pieces of information put together gives you the structure. That is what spectroscopic analysis is. I told you that in order to be a very efficient user of spectroscopic technique, you need to have two properties. You need to have a natural intuition, a capability of thinking out of box. So you should be able to think out of box. You should be able to draw in a structure which you can justify, and a capacity of self-criticism. Both of these would eventually come when you are a well reader, when you read a lot. Because remember, only the readers can think. Thinking is a process which trigger through reading. Okay, even among the NMR spectroscopic techniques, we haven't started the theory of NMR yet, but even in the NMR spectroscopic techniques, there are plenty of technique, and the reason why I want to give you this, because even if you decide to do NMR spectroscopy, at that stage you need to decide which NMR techniques you would use. The reason is multiple, because you have lots of choices of NMR techniques. I told you that the NMR is a science of acronyms. There are so many techniques. Almost all possible combination of alphabets will give you some sensible NMR techniques also. So there are lots of NMR techniques, and you often bewildered, very often puzzled which particular technique you would like to use first. This is my way of thinking. I think that the 1D is the first thing which you would like to do, one-dimensional NMR spectroscopy. Then you go for a two-dimensional spectroscopy, and in two-dimensional spectroscopy, you use correlated spectroscopy to identify coupling relationship between protons. And then in the next stage, you go for one-dimensional C13 NMR. The reason why I don't want to suggest you to go for C13 right away, because of a simple reason, which I told you last time. It's very insensitive, it requires lots of sample, and it requires lots of instrumentation time also. Only when you have these data available, then you go for fancy techniques like carbon-proton interaction, and then carbon long-range interaction. Then you look into the stereochemical analysis, then you look into remember, in structural elucidation, you have a carbon framework, carbon skeleton. On top of most of the carbon, you have a proton. So when you see proton-proton interaction, that indirectly means carbon-carbon interaction. But in order to establish a relationship between proton-proton and proton-carbon, you need to have a proton-carbon spectroscopy. This all HMQC, HSQC, they are proton-carbon spectroscopy. And then once you assemble carbon framework, you want to know what is the geometry of the structure, what is the three-dimensional structure of this molecule. So you use nuclear overhauser effect. And so there are a number of different ways of doing it. I don't want you to I don't want you to be worried about these acronyms. I don't even want you to be worried about the sequence. What I want you to do to understand that in NMR spectroscopy you have lots of choices. And when you have lots of choices, you can make choices only on the basis of knowledge. And that is primarily the reason why you want to learn the elementary basic concepts of NMR spectroscopy. This is precisely the reason why I want to take you through this process. And same thing in a more elaborate way. There are plenty of one-dimensional techniques. There are plenty of multi-dimensional techniques, and you can make a very complex tree of them. Lots of them, but only few of them are required for most of the problems. And which few of them is your own understanding, which you would eventually decide. But let's go through the fundamental of NMR spectroscopy, and I want to give you I want to give this a title which we use in our book called Birth of an NMR Signal. Why an NMR signal is born. What are the fundamental of the birth of an NMR signal? And these fundamental concepts are given in a largely a non-mathematical term. So, if you want to understand NMR with reference to so-called quantum mechanical theory, so-called physics, then there is lots of mathematics. You go into the NMR books, a lot of these NMR books which were written earlier, mostly by physicists, seems to be like mathematics book, because there are lots of equations, there are lots of theories, there are lots of derivations of equations. But we will essentially use only a few of them, and we would use a more practical approach, which is called pictorial approach, picture approach. So we will use the pictorial approach towards understanding NMR spectroscopy, because this is found to be the most effective way of understanding NMR spectroscopy to the user's level. I'm not saying that if you are doing an NMR spectroscopy, a PhD in NMR spectroscopy, you would adopt this situation. You won't do it, because then you would go for hardcore mathematics, you would do lots of other things also. In order to understand at a user level, we would go for a pictorial diagram. And I want to start with a simple fact. You see, number of electrons in various elements are very fluid. I told you earlier that they defined the charge, the radicals of different things. You can have a phosphorus plus 5 charges, or plus 3 charges, or 4 charges, or whatever. You can have different balances, but phosphorus remain phosphorus. Even if you take out 3 electrons or 4 electrons, or if you add 1 electron, an anion, they remain phosphorus. So electrons define, always remember, electron define the character of an element. Radical, charge, reactivity, it's defined by proton only. The same number of protons would make same number of elements, same elements, so you can have different number of electrons, but if they're same. Neutrons define the isotope, right? So neutron is a characteristic present of neutron. Defines isotopic nature. All of these species, without any exception, exist in spins. So, and the spins are of making stabilization protons, electrons, all of them exist in spins. When they are spin paired, a very important discussion, when they are spin paired, they are spherical in nature because there is absolutely no distortion in their charge distribution. Everything is counterbalanced. When they are not spin paired, either because of the Nagin odd number of neutron, odd number of proton, or both of them, or one of them, unspherical nature arise in the elemental nuclei, right? Spin pairing make an element spherical, and spin unpairing of either proton or neutron or both of them or one of them make a nuclei non-spherical in nature in terms of magnetism. And that particular property, this particular physical characteristic gives them a very special character which is called nuclear spin, So please try to remember that odd mass or odd or even or odd atomic number will give a spin quantum number half 3 by 2 5 over 2. But if both of them are even, they are spin paired, and when they are spin paired there is no spherical, there is 100% spherical and there is no spin. And if one of them is even or odd, you would have 1 2 3. So only those nuclei in periodic table would have spin properties which have either odd number of atomic mass or odd number of atomic number, right? Or more precisely, odd number of protons or odd number of neutrons or one of them, right? So if I ask you a question that you faced with an absolutely grieved situation as an organic chemist, that most desirable element, carbon, is spin paired. Therefore, it is NMR inactive. It's called NMR silent. For consolation, nature has been very kind to you. That proton, which is also one most beautiful element in the world, is all NMR active because it has one proton, or it has so this is NMR active. I want to tell you something very interesting. God has given us an amazing capacity of analyzing every element by virtue of the fact that at least one isotope of every element is NMR active. Okay, so carbon 12 is not NMR active, but carbon 13 is. So you can literally analyze every element in the periodic table by using the desirable isotope. The problem is that very often these isotopes are very dilute. The abundance is very, very small. For instance, in case of carbon 13, it is only 1.1%. Right? So now, as an organic chemist, you have two elements which you would like to analyze in your molecule. One is proton, which is NMR active, and one is carbon 13, which is NMR active. Carbon 12 is NMR silent. This is how you want to. This nuclear spin is an extremely important property, and this nuclear spin is directly proportional to the spin quantum number and with the proportionality constant of so-called gyromagnetic ratio. We would understand what gyromagnetic ratio. You would find it a different name, magneto-gyric ratio or gyromagnetic ratio. The most recent one is gyromagnetic ratio. Okay, so this nuclear spin, so-called angular magnetic moment, is equal to the gyromagnetic ratio, the spin quantum number, and the Planck constant, which is a fixed number. and that's how you identify your. Now, you see, this is the property of the nuclei. You see this nuclei? It is actually moving around its own axis. Its own axis. This is the spin. So there is one axis, and this is this axis, right? And this is a vector quantity. Remember vector quantity because it has a direction and a magnitude, right? And it is moving around it. It is around it, so it is a angular spin. Angular spin. This is the angular spin. What is not happening that this axis itself is stationary. Axis को कुछ नहीं हो रहा. The axis is stationary. The only thing which is happening without a magnetic field is this particular element which is spin, right? And this spin is this particular spin called angular spin, right? Simple, carbon 12 has a zero spin, proton half spin, and therefore by using a very simple formula 2i plus 1, you know that it would exist in two states. Deuterium exists in three states. Carbon is NMR silent. Carbon 13 would exist in two states, 2i plus 1. Very simple equation. Oxygen 16 by virtue of again neutrons and paired proton is NMR silent. O17 on the other hand is NMR active because it has the odd number of neutrons. And where is the odd number of neutrons, this is the spin quantum number, and if you fit into it, you would have a 6 different states. Fluorine 19 exists is again a spin half and it in 2 different states. Your attention is required. This particular 2302362 is a very important. If you want to simplify your life, you say that that we want to deal with proton and carbon 13, and both of them have only 2 orientations, right? They exist in 2 quantized state. That is the quantum mechanical description. Deuterium exists in 3 different quantized states. Nitrogen 14 exists in 3 different quantized states. Oxygen 17 exists in 6 different quantized states. And nitrogen and F19 exist in 2 quantized states. Now these quantized states are the one which are not visible without magnetic field. खत्म खलास मैं जा रहा हूँ. Okay, you see, they have the property of existing in 2 different. One can exist. We would be repeating it several times, so don't worry about that, because this is what we would discuss. This exists either high energy or low energy, only 2 states. Exist in 3 states, lowest, in between, and the highest, right? Carbon exists 2 states, plus half, minus half. Nitrogen exists in 3 states. Oxygen O17 exists in 6 different stages, right? And fluorine exists in 2 different stages. I don't know whether it really make any sense to us or not, but among all these states, the lowest is the one which is closely aligned to the magnetic field, and the highest is the one which is most opposing to the magnetic field. Life becomes much easier when you have spin half nuclei, because you deal only plus half and negative half. Please don't worry, मैं चेहरों पे परेशानी देखने का कायल नहीं हूँ, क्योंकि वो क्या शायर कहते हैं कि जिस कदर हम हैं परेशान. Elements with either odd mass or odd atomic number have the property of nuclear spin. The number of spin state is, inshallah, explain to you right now. Can exist. That is what I am going to explain right now. Okay, when there is no magnetic field, the reason why people were not able to discover the NMR phenomena for a long period of time, although the strange behavior of under the magnetic field was discovered by Zeeman at the end of the 19th century, but nobody was able to understand that it can really lead to an absorption of energy. But I want to example. This is assume that they are your proton nuclei. Protoni कहते हैं. The language of NMR spectroscopy, hydrogen is never hydrogen. है ना? बड़ा unfortunate है. Just one proton. I forgot literally. इनका word में भूल गया. Just we always use proton, one proton. Okay. So these proton, without the magnetic field, have an angular moment and a direction. But this direction is absolutely discrete, degenerate, and without any fixed orientation. They are moving, each one of them is moving along their own axis. Along their own axis, which axis is stationary. So all of these nuclei are randomly arranged all over, and there is absolutely no distinction between these two states which I mentioned to you. Two states of either plus half or minus half. Two states are not. These two states are not visible without the applied magnetic field, right? When you apply the magnetic field, two things happen. Number one, this is the applied magnetic field, conventionally called P naught. Conventions are extremely important because we always need to remember they are always in the Z positive direction. The Z positive direction, long time ago, NMR spectroscopists decided to orient the magnetic field, explain them with reference to Z positive. So this is your magnetic field, okay? This is your magnetic field, P naught. More precisely, in the language of physics, called magnetic flux density, because this is basically a flux of magnetic field. So this is your applied magnetic field. Applied magnetic field, never forget it. Without applied magnetic field, there is no fun in life, right? When you apply magnetic field, either by permanent magnet or by an electromagnet or by a superconducting magnet, two things happen. Number one, these all nuclear species of proton either orient themselves along the magnetic field or opposed to the magnetic field. Okay? So now you have one thing established, that these two states are now clearly defined. Exactly the same experiment as you used to do, that when you bring a permanent magnet and if you have lots of pin, they all arrange themselves in a particular direction. They kind of small pins hoti hain, which you use in the paper, they arrange them in a very particular direction. Now this thing is called oriented state. And since this is a spin half nuclei, you have only two states, either aligned or opposed, right? But you can have 3 states, 4 states, 5 states, 6 states. Remember, when you have 4 states, the lower one are the one closest, relatively less closest, relatively less opposing, more opposing. Okay? So this is the quantized states of, but spin half nuclei have all nuclei, spin half nuclei like carbon 13, proton, or fluorine, they all have only two states. And these two states are plus half or minus half, highly oriented. Okay. The reason why they do it, a very simple reason. Number one, because they already exist in a different states of energy, but they are not oriented. Once they are given an external field strength called magnetic flux density, they go to a particular class. Okay? That is the basic fundamental. So that's how it actually happens. I told you only one thing right now. When you place your magnetic field, when you place your sample with spin half nuclei like proton, they orient themselves into one of the two directions, either two directions, right? The other thing which actually happened, which is the most fascinating phenomena, is their angular momentum would not remain be stationary, but they start precessing around the direction of B naught. Okay, around the direction. Remember, without the magnetic field, they were orienting like this. They were spinning like this at a different direction. But when they are placed under the magnetic field, the first thing happens that they orient themselves one of the two states. And the other thing which actually happened, that along with the spin, they also start spinning around the applied magnetic field, which is B naught. So this is your B naught, and this is the Z direction, which is conventional direction of the B naught. Now you have two different frequencies. One is called axial movement, the other is called angular moment, and the other is called axial movement, right? So this particular movement is called Larmor frequency or Larmor movement or precision frequency, the number of different names. Okay, the frequency is now very. I want to ask you why it actually happens. You know, why under the influence of a magnetic field they start precessing like this? Why? Simple fact. They are all magnets, right? And a tiny little magnet under the influence of a strong magnet can only survive by dancing around its direction. Physics is called torque or a motor function. Torque कहलाती है. Torque of fundamental physics. When you force a nuclear species or any species to turn towards the direction of particular direction, and then it start moving. So this turning is a torque, and this is the survival tool called precision frequency. This precision frequency, इसको क्या कहेंगे? ओमेगा कहते हैं, क्या कहते हैं? हैं? ओमेगा कहते हैं. अच्छा, still remember. So this particular frequency has several names. Scientific name, precision frequency. This particular process called precision. ये वो precision नहीं है of precise. This is a precession. Okay. It's not precision, right? It's a precision frequency movement, right? Precision frequency. Precision process. Frequency of the precision is called precision frequency. More precisely, in order to honor the name of the person who first discovered that, Joseph Lama, who was a physicist, this is called Larmor frequency. Larmor frequency. Okay. Now, here a bit of mathematics. This precision frequency is directly proportional to B naught. Directly proportional to B naught. It has lots of bearing. This is the foundation we are trying to lay to understand the elemental fundamental of NMR spectroscopy. Okay. So is directly proportional to the V naught, and the proportionality constant is gyromagnetic ratio. Okay, which primarily means that in high magnetic field, the precision frequency would be higher, right? A direct relationship. If you have a magnet of 3 Tesla, and if you have a magnet of 5 Tesla, or 7 Tesla, or 18 Tesla, the precision frequencies would be directly proportional to the magnetic power, B naught. Okay? B naught. Magnetic flux density. Okay, and this proportionality constant is a gyromagnetic ratio, which is extremely important. Gyromagnetic ratio is a property, inherent property of an element which determine the response of an element towards the magnetic field. It's called magnetic field susceptibility. How susceptible they are for the magnet. How susceptible they are for the magnet. Very easy concept. You bring different metals in front of a metal, and different metals would have a different affinity for the magnet depending on their own inherent property of magnet. Here we are talking about spin half nuclei. Proton is 4 times more susceptible for magnet as compared to carbon-13. Carbon-13 gyromagnetic ratio is 1/4 of proton. It simply means that if you have a 10 Tesla machine, and if your proton is moving, this precision frequency is 600 megahertz, the carbon-13 would move with what direction? With what speed? 1/4, which is what is 1/4 of 600? God, what a mushkil. God, I mean, it takes about 1 hour to understand. Huh? 1/4 of 600. 150, oh God, you're so smart, mashallah. Okay, so the same magnet, but different elements behave differently on the basis of their magnetic field. If I tell you that I bring a magnet which is 20 Tesla, let's say, what would be the precision frequencies of proton? Double K exactly. 1200, huh? 600 tha, na? 1200. And carbon-13? God, I've never seen smart people like that. Okay, so that gives you a direct relationship between the applied magnetic field and the precision frequency. Very, very important. Because remember, that would have a bearing as we would move forward. The reason why people have invented and developed high field magnet was precisely the same thing, right? For carbon-13. So, is a resonance frequency or precision frequency or longer frequency, whatever, gyromagnetic ratio, external magnetic field, two orientations. One is towards the direction of the magnetic field, which is called low energy state, because this is aligned to this field. This is aligned to the magnetic field, and this is opposing to the magnetic field. I'm really sorry, इसको नीचे होना चाहिए, मगर Z तो ठीक ही है, वो इसका जो direction है ये नीचे है. This is alright. This is opposed to the magnetic field, or non-aligned to the magnetic field. Okay. And you can have lots of different stages. So okay, this is the. At this stage, I want to take questions, because I think it's important for us to understand what this concept means. Two things happen. What is these two things are? Orientation and precision. Orientation and precision. C12 has a spherical charge distribution. It is not magnet. It's not really. It doesn't have any character to behave like a spin. Okay. Now I want to ask you a question. एक बड़ा simple सा question है. My question is, if question anyway, question कुछ तो पूछना है. My question is the following. In a greater field strength, uh, would there be any effect on gyromagnetic ratio? Let me ask you a question. On which two factors the precision frequency based? Which one is in your hand? Which one you can increase? That's what they did. Finish. That's how they were doing it. That is the reason why they have developed the high field NMR. That is what they want to do. But what would eventually happen if you have a high field NMR? If they are processing faster, then what is the difference? क्या फर्क पड़ता है? What is the difference? You can see is directly proportional to the magnetic field, applied magnetic field. Stronger the magnetic field, more the precession frequency, right? So what? This is the problem of having a student who knows animal, right? So I think we should really screen them out. Okay. I don't want you to. I don't want you to understand that at this stage. The only thing which I want you to do is to understand that precision frequency is dependent on two factors: gyromagnetic ratio and applied magnetic. And I also want you to understand that the applied magnetic field is the one which you can change, modify, increase, or whatever. I want to ask you a question. Precision frequencies of all proton in one fixed magnet would be same or different? Why different? All protons are protons. But they all have a different electronic environment. God, this is a problem. Okay. The proton, hydrogen nucleus is the most studied, most important nuclei. Most important nucleus. Most important nucleate. The NMR language called nucleate. This is the most important nucleide because a lot of NMR spectroscopic techniques are based on detection of proton, detection of proton. You see this interesting thing? See this नजर आ रहा है वो छोटा सा एरो? Right? And this is plus half and this is minus half. Done? Shall I go forward? Spin. Two different movement. One is angular, the other towards the axis of. If I tell you that Earth is doing the same thing, you would believe me? Earth is moving along its own axis, which create day and night. And Earth is moving along the axis of Sun, which creates weather. Huh? Right? क्या? Seasons and weather. चलो, I accept. क्या? Years. Good, thank you. Years. Day, night, years, weather, seasons, everything, right? Okay. Two moments, right? Exactly the same magnetism at a macroscopic level. And this is the microcosmos of the universe. Microcosmos of the universe. A macro level movement of the same philosophy, exactly the same. Earth has its own magnetic field. Earth is a magnet. It has a vector. It has a vector diagram. It has a vector, and it is moving along its own axis, and it moves along the axis of a larger magnet, applied magnetic field, which is Sun, right? That is the closest and the most beautiful example of micro level movement and a macro level movement and a micro level movement. Okay. Now, question: without applied magnetic field, the energy difference between them is negligible, not really much. When you apply the magnetic field, they orient themselves in two directions, right? Spin half nuclear, and they precess. Precision go, you just forget the precision for a while. The difference between two energies, two levels, the aligned and the opposing, is del E, the energy difference. And this energy difference is directly proportional to the V naught. Now new factors are coming in. V naught is not only affecting the precision frequency, V naught is also affecting the difference between the energy levels. So stronger the magnet, the larger the energy difference between 2 states, 3 states, 4 states, 5 states, 6 states, whatever. Right? That is the relationship. This is directly proportional to V naught, right? Now, what happens when a spin active hydrogen atom is placed in a strong magnetic field? It begins to persist. Now, this is the fundamental fact which we would like to know. You see, in NMR spectroscopy, this precision frequency, I ask you a question that why physicists were disappointed because their understanding was that all the proton should have a same precision frequency, right? But it is not the case. The precision frequency is not the same, although all of them are experiencing the same magnetic field. V naught is same for them, but their precision is different. And this precision is different because of their electronic environment. This is the reason why chemists were so happy to see 3 peaks for ethanol, because they know that these 3 different types of hydrogen have a different electronic environment. So electronic environment make precision frequencies different from each other. Now, the only thing which you need to measure in NMR is precision frequency. If I tell you that in ethanol, the precision frequency of methyl and the precision frequency of CH2 and OH is different, and they are different because of their electronic environment, that's what you need to know. Question is how you will measure it. Can you measure precision frequency? Can you measure precision frequencies of ethanol, 3 different hydrogens? 3 different hydrogens, all experiencing the same magnetic field, but have a slightly different precision frequencies, and I'll tell you why. We would deliberate upon it because we need to discuss this for the sake of everyone. They have a different precision frequency, slightly different precision frequencies. The magnetic field is in Tesla. Overall response is in megahertz. The difference in precision frequency is only in hertz, which is 10 to the power minus 6. So is this little difference in precision frequency is what your NMR is. But do you have any method of measuring the precision frequency? You don't. Absolutely no method. If we have, we don't need to do anything. Believe me, you just place your sample under the influence of magnetic field. You don't need to do anything with it. You just measure the precision frequency and you will know precisely what is. Ethanol, 3 different precision frequencies. Cholesterol, 46 different precision frequencies. Right? Benzene, 1 different frequency because all protons are similar. Toluene, 5 different frequencies. Precision frequencies, different. Why? Can we measure precision frequencies? We can't. This is the reason why everything else was developed. If we have the capacity of measuring the precision frequency of nuclear spin under the influence of a magnetic field, we don't need to do anything else. The only thing is that we cannot do that, and since we cannot do that, we need to proceed forward. Kuch na kuch karna padega. We need to do something, and that kuch na kuch is bringing another energy, and that is your radio frequency. Radio frequency. Remember, your magnetic field is not going anywhere. It remains there. External magnetic field, applied magnetic field, magnetic flux density is an ever-present entity. You always have that. Without this, you cannot create a condition in which you can play with the radio frequency. You bring radio frequency at this stage because now you have set this stage for absorption. You cannot absorb energy when there is no difference in energy levels. You can only absorb energies when there is a difference in energy levels, right? And the difference in energy level was set through the presence of applied magnetic field, right? This is the radio frequency which you bring, right? You do it perpendicular to the direction of the applied magnetic field. This is your low energy state aligned to the magnetic field, and this is your high energy state opposing to the magnetic field. And radio frequency must match the precision frequency. Remember the concept of in resonance. Always remember the concept of in resonance. Always remember the fundamental fact that electromagnetic radiations have 2 oscillatory fields, electric and magnetic. Both are in absolute in phase, perpendicular to each other, and they carry photon, right? And this photon is the energy, and the energy of photon is directly proportional to the wavelength of electromagnetic radiation. In order to transfer this photon from radio frequency to the receiving matter, you must have in resonance. In resonance means that they must oscillate with the same frequency. Okay, so only the radio frequency photons, energy would be absorbed when it will match with the precision frequencies. Right? Yes or no? Classical example which Professor Tarmans gave. These are frequencies of radiations. This is your radiation, electromagnetic radiation, and this is your receiving field, so-called precision frequency. The transfer of, and you're holding a sandwich, which is your photon. Okay? Energy. Sandwich is energy, right? So you can transfer this sandwich to the other hand only when you have a matching frequency. Then you can transfer. NMR में बड़ी exercise बड़ी हो जाती है, बाजू बड़ी मिलती है. Okay. So that is called in resonance. And in resonance, always remember, is a cross-cutting phenomena in all spectroscopic technique. In all spectroscopic technique, everything is relevant to in resonance. Until you create a situation of in resonance, you cannot have a constructive interference with the matter. Right? Constructive interference to the matter would only take place when you would have in resonance. So this process is called resonance. And that is the reason why the technique is called magnetic resonance, nuclear magnetic resonance, right? Nuclei, magnet, and resonance. Whole concept within 3 alphabets, NMR. Okay, so this is called nuclear magnetic resonance. Problems. There are problems, you know. For instance, proton is about 100% available, right? 100% available. Only very little of it, 0.1%, is deuterium. The rest is all proton. These are the magnetic fields. Magnetic field of applied magnets. Field of magnet. Remember, applied magnetic field density. The unit of magnetic field density is Tesla, right? 1 Tesla frequency is 42.6. 1.4 Tesla 60. 2.34 100. 7.05 300. Directly proportional, right? With reference to gyro-magnetic ratio. So this is, इसमें कोई मुजात है? Problem तो नहीं है ना? नहीं? C13. Abundance is only 1.1%. Okay? Same magnetic field as you had here, 1 Tesla. The frequency, precision frequency, the average frequency, precision frequency of carbon-13 is 10.7 megahertz, right? At 2.34, you increase the magnetic field, the precision frequency increase. Accepted fact, right? When you go to a 7.05, this is 75 versus 300, the same 1/4 ratio of gyromagnetic ratio. The between this and this is 1/4. Okay. Any question? This I wanted to show you in order to make you realize that this relationship has a quantitative meaning. You all agreed with the fact that precision frequency is directly proportional to the applied magnetic field and gyromagnetic ratio, right? Dependent on the gyromagnetic ratio. You see, the increased magnetic field will have an increased precision frequencies. But this increase in precision frequency is governed by gyromagnetic ratio. Okay. This is the Larmor equation which I want you to understand. Frequency of the incoming radiation. Remember, frequency, precision frequency of a nuclei need to be exactly matched with the radio frequency in order to have an absorption. Therefore, W naught and precision frequency is exactly the same, right? And it is directly proportional to the gyromagnetic, to strength of the magnetic field, applied magnetic field, and gyromagnetic ratio, right? Remember also the difference in two energy state of a spin half nuclei is directly proportional to applied magnetic field also. This is the relationship. Why you need to have radio frequency? Because you want to measure the precision frequency. There is absolutely no reason for you to do anything else if you know how to measure the precision frequency without interfering with the system. You can measure the precision frequency only by bringing an external factor, which is your radio frequency. And radio frequency is absorbed to the system when it is in resonance. So for instance, if there are 3 different types of protons in ethanol, there would be 3 different types of precision frequencies, and radio frequency would be absorbed at 3 different positions, and you would have 3 different peaks. plain and simple. Life is so easy, right? Nahi. God, life is not that easy. I agree. Question. Any question from the other places? Please feel free to, because I think we are moving forward and we want to make sure that we have a solid foundation of resonance. This would increase directly proportional. Very, very interesting question. The difference between the energy levels of 3 protons of ethanol would be same or different? Different. How much different? In megahertz or in hertz? In hertz. Right? Very slightly hertz. Because the concept which I am going to introduce is the governing factor, and that is called B effective. जो मैं आपको भी थोड़ी देर में I will discuss that. What is B effective, and that would tell you why the precision frequencies of 3 different types of protons in ethanol are different. Physicists were not happy with it. Chemists were extremely happy because they understand that these 3 protons of ethanol would have 3 different precision frequencies. 3 different precision frequencies because of their electronic environment, and therefore the B naught is not same for them. B naught for them is slightly different. And when the B naught is different, the difference in energy is also different. That is a problem. Be effective. We are coming towards that actually. We are actually moving towards this direction. Or I'm just dying to give you this famous example which I always love. Which one? Oh, good. I like this example. मुझे लगता है कि the only reason why I like to discuss NMR is because of this example. Okay, so we move forward. Absorption of energy by the spinning nuclei, and that's what actually happens when you have a strong magnetic field. When you bring radio frequency, a condition of resonance takes place, absorption takes place, the aligned one goes into the opposing directions. From one energy state to the second energy state, from low energy state to the higher energy state, there is a need of an absorption of energy. And this absorption of energy is your NMR signal. Is your NMR signal, right? Okay, very simple. This is aligned to the magnetic field, and when you give energy, it becomes opposed to the magnetic field by absorbing radio frequency, and the difference between the two energy state, difference in the two energy state is directly proportional to the B naught, right? Now, I want to take you to the world of instrumentation because this would really facilitate our learning process. Classical instrumentation before 1960s. Before 1960s, NMR spectrometers were more or less like UV spectrophotometers, IR spectrophotometers, with the only difference of magnetic field. The rest was same. If I show you the instrument, it was very, very simple. You have a magnetic field, you have applied magnetic field, you have a sample tube, and you have radio frequency oscillator, generator, which primarily means energy source, and then you have a radio frequency detector, and then you have a recorder, the recorder, right? So for instance, if your sample has 3 different types of proton, you would have 3 different types of peaks. Right. Now, it started with amazingly simple instrumentation. If you go to internet and if you look into classical NMR instrument, they were like radio, magnet, open magnet. You have your sample in it, and then you increasing the radio frequency. Remember, this is a permanent magnet. Permanent magnet. Permanent magnet, ethanol, 3 protons, 3 different types of proton of ethanol have 3 different types of precision frequencies, slightly different, right? So when you bring radio frequency and you have a radio in your hand and you increase the knob, you move the knob and increase the radio frequency from less to the more, as soon as it fit, you see an absorption, right? No? As soon as it matches with the precision frequency of methyl, you see absorption. Move forward. As soon as it reaches to the frequency of CH2, you see an absorption. As soon as you move to frequency of OH, you see an absorption. You see a 3 peaks. Question. You have a constant magnetic power and you are sweeping radio frequency. It's called continuous wave NMR spectroscopy. Is exactly the same as you do UV, because in UV also the radiations can be photodiode array. IR, you increase the IR, you have a different frequencies of within the IR band also, and you see the absorption. If I give you the option that now I am more developed and I have developed an electromagnet. I have developed an electromagnet. In electromagnet, I have the capacity of sweeping the magnetic field also. Right? Yes? Who knows electromagnet? Everybody knows about that. Electromagnets are magnetism controlled by electrical power. Right? So we have the capacity of increasing the magnetic field. Now you are sitting in an instrument company and you are designing a new instrument in which you would like to design an instrument which is more reliable. You have an option of having a permanent magnetic field, electromagnet, fixed electromagnet. You have a fixed electromagnet, and then you sweep the radio frequency. Or you have an option of having a radio frequency of a constant length or a breadth of a length, and then you have a power capacity of increasing the magnetic field. Which one you would opt? Constant magnetic field and changing radio frequency. And this is absolutely wrong, because electromagnetism is a much more controllable phenomenon. It's a much more controllable phenomena as compared to radio frequency. Simple reason. Radio frequency is, always remember, radio frequency is a very weak radiation. Very weak radiation. Magnetism is in a strong quantity at Tesla, which you can control, and therefore plus minus deviation is tolerable as compared to radio frequency. So what you would do, I invite you to think over it. You have a constant radio frequency, right? And then you sweep the magnetic power. When you increase the magnetic power, the precision frequency would also increase? Yes or no? And as soon as it matches with the radio frequency, absorb, done. Good. Yes, no. As you turn on the electromagnetic, as you turn on the electromagnet, the situation creates. Two state would be there, but the precision frequency would changes with the electromagnetic radiation. No, it won't take as a it would function as a radio frequency, but as soon as the precision frequency matches with the radio frequency, you would see an absorption. Therefore, the magnetic field is increased. We are changing the magnetic field, and as we changing the magnetic field, the precision frequency is also increasing. And as soon as the precision frequency matches with the applied radio frequency, then you see an absorption. Okay. Increasing the power of magnetic field.
Yes, ऐसे ही हाँ फिर डिस्ट्रक्टिव हो जाएगा फिर रिजल्ट्स नहीं आएगा ना
They are changing the we have a magnetic field.
Make them align or
No, we are not changing. See, we are slowly increasing the magnetic field. As we slowly increasing the magnetic field, the precision frequency is also increasing. And as matches with the radio frequency, you will see an absorption. As soon as the precision frequency of CH2 matches with the applied radio frequency, you will see an absorption. So there are two ways of doing it. Either you have a permanent magnet. In permanent magnet, you don't have a choice. In permanent magnet, the only thing which you can do is to sweep radio frequency, right? And in the electromagnetic radiation, in electromagnet, you have the capacity of increasing. Excuse me, if you have any question, please ask me, right? If in electromagnet you have the capacity of increasing it. See, precision frequency is directly proportional to, you have, let's say, 300 megahertz applied radio frequency, right? And you are slowly increasing the electromagnetic power. There would be no absorption until the precision frequency become 300, right? That's how you sweep it. The other is 300.1. Then in that case, you increase the electromagnetic radiation to a level, electromagnet to a level when the precision frequency of the other is absorbed. That's how you do it. So sweeping of either the radio frequency or magnetic power were different options. In permanent magnet, the continuous wave NMR spectroscopy, you didn't have any choice. Only choice you had was only radio frequency. But when people have developed electromagnet, they have the capacity of increasing the magnetic power. Number one, larger magnets were designed, and number two, you can control, you can sweep the electromagnetic radiation, and instead of a radio frequency, the radio frequency band is applied. It has a bearing because now, as we move forward, we will understand why it was important. Development like this, why this conceptually. So now magnet was changed with the electromagnet, and now electromagnets have been changed with superconducting. The change in magnetic magnet is most wonderful physical development. You see, the physics of magnet has fascinated lots of people. Magnets has been a very, very interesting topic. And superconducting magnetism and superconducting physics is altogether a different field which has attracted. Superconducting magnets are the magnets which are made of special, very special alloys. For instance, niobium. Niobium is an element. Niobium coils है. Niobium coils होते हैं, and when you merge these niobium in a very cold environment, very cold liquid like helium, which is the coolest thing on the face of the earth, minus 269 Kelvin or centigrade, at this particular temperature you give electricity to the niobium coil and turn it off, and this remain magnet, because at that particular temperature the magnet has close to zero resistance and close to 100% conductance. This is your superconducting magnet. Beauty of this superconducting magnet was that you were able to design larger and larger and more stronger magnets by using it. Because permanent magnet has a capacity, electromagnet has a capacity, superconducting has absolutely limitless. So very high magnetic power depending on the quantity of alloy of lithium. So that's how the superconducting conducting magnets were designed. Now, always remember that magnetism, even in the most advanced magnet, there is a problem of inhomogeneity. This inhomogeneity, magnetic power, is not 100% homogeneous. And this is the reason lots of things which has been done, which I'm going to tell you. But always remember that the most important development which took place initially was based on your understanding that the precision frequency is directly proportional to the magnetic power, and that was the only thing you could do at that time by designing a larger and larger. Okay? This was the basic phenomenon for the magnet. Now, again, construction is shown. Construction of the conventional 60 megahertz machine is shown. This is a magnet, and this is a probe. Probe is a metallic cylinder. It's a metallic cylinder in which you place your sample. And this metallic cylinder, around this metallic cylinder, you have two things. One, radio frequency oscillator, which gives radio frequency, and the other is radio frequency detector, which detect the absorption. These are two things, and you see by yourself that in the probe you have oscillator or transmitter and radio frequency detector. I'm going to tell you that this theory is absolutely wrong. We do not detect radio frequency anymore. Therefore, there is a reason why NMR spectroscopy started as an absorption spectroscopy and later changed into something entirely different. Very, very different, because radio frequency detectors do not really detect radio frequency. They detect the electrical impedance, so-called electrical alternating current. But you don't need to worry about it. We will go and visit this thing again and again. Now, this is very important. The classical NMR experiment in the low field to the high field. You had this property of either ability of either suiting the radio frequency or by increasing the B naught, electromagnetic radiation. Right? That is how you used to record conventional NMR. And example, if you have a molecule like this, and you are in 1960, you are using a continuous wave NMR spectrum, and you have a molecule like this. Can you see it clearly? You have CH3, then you have a carbonyl, and then you have a CH2, and then you have a phenyl, benzene group with 5 protons. Right? And all these 3 protons have 3 different position frequencies. 3 different frequencies. These 3 different precision frequencies need to be in resonance with the applied radio frequency. The radio frequency which is here. As soon as the radio frequency matches with the precision frequency of this, you would have an absorption. As soon as it matches with this, you have an absorption. And as soon as you would have a matching of the radio precision frequencies of phenyl proton, you would have an absorption of. You see three different signals because these are 3 different types of protons. Now don't ask me that phenyls are different. This was later, long term after, when people would be able to distinguish between them. Earlier, the phenyl protons were coming as a, because this was a low resolution NMR spectroscopy. Low resolution. See 3 different signals. I want to invite you to think that even if you are working on a very simple equipment, and if you have from 0 to 10 scale, you are recording mainly the baseline, isn't it? There are only 3 occasions when you see your pen move up. Most of the time it is the baseline. And you are extremely careful because you don't want to turn the knob very, very fast. You don't want to do it because of a simple fact: you will miss out, you would have a distorted peak, and if you're lucky and if you're seeing some splitting due to coupling, you will not be able to record it until you're extremely careful and moving this knob very, very slowly. Right? So, most of the time you are recording the baseline. This was a problem. A normal absorption NMR spectroscopy had the most important disadvantage, and this disadvantage was that you take lots of time to record one NMR because most of the time you're recording the baseline. You're recording the baseline of it. Now, at this stage, I would like you to ask me questions, if any, up to here. The chronology of development, of NMR instrument, because after that, exciting things will start happening. You see, you have three different protons. You have 3 different protons. Huh? 3 different protons, and these 3 different protons, assume that you have a radio frequency band, applied radio frequency band constantly, right? When you would when you will increase your radio frequency, or when you increase your electromagnetic radiation, the precision will also increase. And when the precision of this metal will matches with the component of radio frequency, it will absorb. When it matches, then it will absorb. When it matches, this will absorb. So, by varying both parameters, you can record an NMR spectrum, and people found it more controllable to move the electromagnetic radiation, electromagnets, rather than radio frequency. More stable and better. I will tell you why it's expensive, and I'll tell you because the theory has changed. The theory has changed a lot, and this is not the one which we do now. We do not really do. We are not really recording absorption and mass spectroscopy. This is the most important development. You see, the landmark, anybody from the remote location, if you want to ask any question, please.
Dr. Saab, I have a question that with reference to this spectra, we have 5 protons for phenyl group and 3 for the methyl group. So, but the intensity is the same. How we can differentiate that the number of protons?
Intensity, integration. Intensity can be anything. Integration make the difference. You can have a very long peak of 1 proton and a very short peak of 3 proton. The area under the peak is called integration. Area under the peak, which define the number of proton. If your question is that they look exactly identical, they don't actually, because the area under this is more than the area under this. And use the classical method of measuring the integration, because they didn't really have sophisticated instrumentation at that time. They used to cut the peak and weight, and the difference in weight in the weight was difference in integration. Area under the peak. So again, one confusion need to be, kindly remember that you can have a very sharp and long peak of 1 proton, and you can have a broad and a small peak of 4 proton, 5 proton, 10 proton, 20 proton. This is the integration which makes the difference. And this integration is the area under the peak. Area which is covered under the peak is called integration.
Sir, for the new compound with which we can compare, how we know that how many protons of a particular type are present?
Number one, you rarely have a situation in which you can see all the protons as separate signals, because most of the compound you would have some overlapping. Now, the easiest thing is to look into the downfield region, and this is the downfield region. And I'll tell you why downfield region, I will tell you. In the downfield region, you have less of crowding. This is the least crowded portion of normal NMR spectrum, proton NMR spectrum of compound. In this area of low field, you generally look for 1 proton integration. You look for a peak which represent 1 proton. And for instance, an olefinic proton, a vinylic proton, something like this. You just look into these proton and use this peak as your standard 1 proton integration, and they measure the other peak with reference to it. This is one way of doing it. Now, modern NMR spectrometer are now all equipped with integrations. The modern NMR spectrum would give you integration with reference to number also. You don't need to even have those sliding peaks. There was a time when people used to have green signal like this. Now they would give you that what is the total area underneath, and they would give you the integration. But classical method, which still work very well, is that when you have a proton NMR spectrum in front of you of an unknown compound, you always try to find a neat, clean 1 proton somewhere in the spectrum, and that somewhere is most likely the downfield region.
Thank you, sir.
Because most of the protons are in aliphatic regions with lots of overlapping. OH proton, if it is not deuterated, if it is exchanged, then you don't see a OH proton. And OH proton, always remember, varies depending on the buffer, the acidity, the exchange of different type, the chelation with hydrogen bonding with different. OH is not a good ideal. The most ideal and nice proton as a standard 1 proton integration is generally olefinic. Sweep. Sure. That's what I'm saying. both of these, essentially the same, you need to be extremely slow in order to record the fine structure in all the peaks. That is the reason why this conventional NMR spectroscopy was extremely time consuming, very time consuming. And the second problem was signal to noise ratio. If you have sensitivity problem, if you have very small quantity of a sample, very often you don't know whether this is a noise or a signal. Yes? Basic?
Basic property of proton. Property of protons. My question is that is there any other technique in which we are using proton?
Basic property?
Yes, we are using a basic property of protons.
Nuclei.
Yes.
Yeah. For
is there any other technique instead of NMR where we are using proton? We are taking.
As I know, perhaps not, because neutron is diffracting. Proton doesn't really diffract. Neutron diffraction is a technique, but proton, in my opinion, is not even proton. You see, please always remember that proton, I'm using proton because it is a proton, right? It is nuclei. Always remember it is a nucleus. This NMR spectroscopy is a nucleus, a nuclear spectroscopic technique, because it deals with the nuclei of an element. Okay.
Sir, can we say that these superconducting magnets are actually the permanent one on the basis of the magnetic strength, which is sustainable?
Unless you keep them at a particular temperature, they're fairly stable. But if you lose liquid helium, and if liquid helium slowly evaporate and temperature of the magnet increases, disaster. Absolute disaster. It's called quenching of a magnet. Your magnet, this large magnet in which we have, and remember we have already discussed that liquid helium is required for a superconductance, and in the outer diva we have a liquid nitrogen to insulate with the environment. This will cost you about $1 million. But once accidentally, if you have evaporation of liquid helium because of some reason, nucleum coil brittle, it become a powder, and this $1 million magnet would become a $1,000 scrap. Right? You don't want to do this. This is the reason why precisely every day people monitor the level of helium, and there is a minimum helium level which you always try to avoid, because you always try to refill liquid helium. You want to make sure, and this is the reason why, because you see, cryogens are major problem in developing country. In many countries, liquid helium is not available. When we first bought NMR spectrometer in 1981, the first cryogen, so pehle we had a permanent magnet NMR, 30 megahertz. People were saying that you would never be able to run it. But we were able to do it because we made sure that liquid helium used to come from Switzerland. And our vehicle used to go directly to the aeroplane to pick the diva directly from the plane to bring it to the HEG Institute. And then when we realized that it is not it can be disastrous because you may really not get the liquid helium on time, we develop our own system in which when liquid helium evaporate, it convert into gaseous helium. And gaseous helium is now collected in our institute. We have a large balloon, half of this room we have a large balloon, and we collect all the helium into that large balloon, and then we repress it, re-liquefy it into liquid helium. So we practically de-liquefy every evaporated liquid helium. Still have lots of losses because you can't recollect all of it, but it is one way of making sure that you have a constant supply of liquid helium. Now liquid helium is available in Dubai. Liquid helium is now, we manufacture our own liquid helium in very large quantities. We can supply to the rest of the country. and is also become a common commodity because MRI requires liquid helium also. So now there are lots of local agents who will give you liquid helium. But there was a time when, so, but the struggle for a long period of time was to design magnets which has a very slow evaporation rate of liquid helium. It's called ultra shielded magnets. U2 कहलाते थे, ultra shielded. So this is the philosophy. Yes.
I have a question regarding what type of material we use for generating we are using what type of material for radio waves, generating radio waves.
Radio waves are electrical coils. Remember, all of these radiations are produced by us by electrical impulses. Are very.
UV tungsten lamp or just like what type of material NMR we using?
I honestly don't know. I mean, probably selenites, something like this, but I don't know. But this radio frequency is generated by using electrical current, and let me check it. I can check it for you, and I'll let you know. Okay. Any question from the remote locations? Any question from Gomal, Sargodha, Karachi University? Okay, let's proceed further. Okay, this was the turning point of NMR spectroscopy, and this is called the pulsed Fourier transformation technology. Pulsed is different, Fourier transformation is different. Pulsed is a technique, Fourier transformation is a mathematics. Collectively is called pulse Fourier transformation technology. And this particular pulsed NMR spectroscopy, pulse is pulse. Pulse means burst, pulse, as we have a pulse, our pulse. See, similarly, in pulse, NMR spectroscopy means energy turning on, turning off, a burst of energy. And in that case, radio frequency is called pulse NMR spectroscopy. It was essentially so important that it changed the whole fate of NMR spectroscopy. Right? Remember, you had only one option to increase sensitivity, and that was increasing the magnetic field. There was a point when people said we can do something different, and that is the pulse NMR spectroscopy. And that pulse NMR spectroscopy requires an absolutely different philosophy and a theory, very different from the absorption spectroscopy. And Fourier transformation was a compulsion. It was required because in order to have a pulse NMR spectrum, you need to have a mathematics which is called Fourier transformation. Fourier transformation, Fourier again, in name of a person. Fourier transformation is a general mathematical calculation. It's also called Cooley-Tukey calculations. Two people who named it after someone. These are equations, mathematical equations, and they are generally used for converting one type of a unit into other type of a unit. But don't worry about that. It's a very, very powerful technique. Now, the modern instrument look like this. This is a 500 ultra shielded NMR spectrometer, and I want you to look it very, very carefully. First of all, I'm going to tell you that these are the legs. You agree? And these legs are very carefully insulated from the vibration. And it is generally underneath this. You see the stairs coming from up? So this is the level, down level. Because as you go down, you would have less vibration. Okay. So these three legs are a way of insulating from the mechanical vibration. 1 one thing. Then you see lots of these things. Circuitry, lots of coils. And under this, there is a probe, right? In the center of this diver, exactly same diver as you use for storing microorganism, for storing cell lines and all that, the same diver. In the center of this diver, you have a probe. And around the probe, you have a magnet. And this magnet is submerged under liquid helium. This liquid helium is stored in a diver which is inside. So there are two diver inside, one outer diver and the other is inner diver. Inner diver contain liquid helium and the outer diver contain liquid nitrogen. This is an area in which you introduce liquid nitrogen because this is for the outer diver, and this is the area in which you have liquid helium. You introduce the liquid helium. You have a probe, so if you want to change a probe, you have to change it from the down. You have to take it out and you have to introduce a probe inside. A long cylinder. But this cylinder never goes more than this because you always try to keep your requirement of liquid helium minimum. Therefore, this whole magnet is just in the bottom. Otherwise, you need to fill this with lots of helium, You introduce your sample from the top. Because this is a liquid, this is a cylinder, and cylinder has only one opening, right, from the top. You introduce your sample here, and when you leave the sample along with the sample holder, this dance, because there is a constant stream of air, bed of air, on which it slowly dances, and it goes down, and eventually quietly sit in the probe. Okay. Now we're slowly understanding why these magnets are so expensive, right? Number two, probe need to be in ambient room temperature because you don't want to freeze your sample, right? It need to be in a room temperature. And just 1.7 centimeter away from the probe, outer wall of the probe, you have liquid helium. Now imagine a temperature difference of 25 degrees centigrade as minus centigrade. What kind of metallurgy you need to have, the whole pinnacle, the most advanced metallurgy which can insulate a probe from such an extremely cold temperature is required. You know why it is expensive, right? Why it is expensive. Then you need to have an absolutely closed diver to make sure that you have a very slow evaporation of liquid helium. Liquid helium will evaporate. It is not possible that you can have a liquid helium for 10 years. There was a time when we used to fill every 15 days liquid helium. We now fill it every 6 months because the better divers are available. Maybe there would be a time when people would fill liquid helium after 1 year. But there would never be a time that you can have a diver which never empty, right? So there is always evaporation. Technology. So you see, the technology is so important. Now, magnet. How you are developing a magnet? You have a cylinder. It's not a probe. Outside the probe, a cylinder of magnetic field, and this cylinder is manually circled. They have a niobium coil, a particular alloy, and they make a circuitry by hand, one after the other, manually. It takes about 6 months to coil this niobium on a cylinder, because you can't do it with the machine. You must really have an absolute sense where you are actually placing it. Reason, you want to make sure that your sample in length is receiving the same uniformity, homogeneous magnetic field, right? So you must make sure that you have a niobium coil. And it is done at a gaseous helium condition. When gas helium is always, and they have a gloves like this wearing, and they are doing it, because niobium will become brittle powder at a room temperature. Then they see the technology. The whole technology is so advanced that NMR are not available off the shelf. You can't buy NMR. You order it and they make it for you. They make NMR for you. This is the reason that every magnet is different from the other. This is the reason that all 300 megahertz NMR instruments in our institute are slightly different from each other. They have a slightly different requirement of liquid helium. They have slightly different requirements of everything, which I will explain later, because they are custom made. They are made for you, and they have a problem with lots of drifting and other. Okay, now you see, this is your NMR spectrometer in which you place your sample and it goes down there. When on the bed of the air, your sample start dancing inside the probe, it has this tube holder. This tube holder fit and spin with an extremely high velocity. Spin. And this spinning was done purposely, because if there is any magnetic inhomogeneity, the effect average out when you spin it. Right? See why it is expensive? So much of it, and this is the state of the art of technologies, So that's what you do, and this is when your radio frequency detector, still using a wrong word, pardon me, because I need to explain what this is. When detector detect the signal, it comes out of it and then it goes through a several cycle of amplification. So there are lots of amplifiers built into this part. Amplify this signal. And when these signals are amplified, always remember these are lines. And when the lines cannot be calculated by the computers. Lines need to be converted into numbers. Lines are analogs. Analogs cannot be handled by computers. Computers can only handle numbers. So the analog lines which are committing out of this NMR spectrometer, amplified, then converted into digital number, and you need to have a very large computer which is called ADC. So you convert analog into digital lines, and then digital numbers are calculated. The digital number is stored in a very large space, and then you do lots of calculation. But essentially, this is your NMR spectrometer. The rest is just processing units. Rest are just processing units, right? This is a new thing which was added only 7 years ago. There's nothing in this dabba. There is one cylinder of liquid helium, insulated. Gaseous helium. This gaseous helium cool down the electronics of the probe. Superconducting probe, so-called cryogenic probe, cryo probe. Superconducting nahi kehte, because this is not a superconducting temperature. This is called cryoprobes. Cryoprobes means cooled probe. So this is the architect of modern NMR machine. Complex, expensive, nice, beautiful.
Sir, I have a question. Like in these modern NMR instruments, what we do when we place our sample, shimming according to that sample, like according to the solvent we have in the sample. For example, if we have chloroform, so we do the shimming according to the chloroform. So here the magnetic field is constant. And so what we are doing here, which parameter we are playing with?
Right. Shimming has nothing to do with the solvent.
Yeah, it's just creating the
Homogeneous
homogeneity.
environment.
So here, like RF or the magnetic field, what we are
I want to tell you. When you change a solvent, you have a deuterium lock for solvent. Every solvent has a different deuterium lock because every solvent like chloroform or methanol, deuterated methanol or deuterated pyridine or deuterated DMSO, whatever, different signals, So therefore you lock it and you are not using internal standards now. So you reference your NMR spectrum from this particular signal which is coming out of a solvent. Initially you used to have TMS and you used to say this is 0, right? Now you have CTCl3 7.25, is it here 7.25, here 3 point something, 3.7, 2.75. So you reference it. Shimming is an extremely important process. You see, always remember that in this magnet, despite the fact that you have done so much of engineering, there is an inhomogeneity. And this inhomogeneity that the magnetic field is not homogeneous, is not uniform. And when I say not uniform, it means really a lot. Please try to appreciate the fact that precision frequency is directly proportional to the B naught. If you have in the sample tube, the upper side of B naught is different from the downside of the B naught, the same proton will give you different signals. Because the B naught would be different and precision would be different. So you need to have an absolutely identical B naught or closest to the exactly identical B naught throughout the sample volume, right? So magnet, how you do that? You cannot change the magnet. What you do, and as your magnet age, the drift and inhomogeneity increases. The coil become aged and problem hone shuru ho jati hai. You would develop an extremely important, extremely nice system that you have around your probe another circuitry. And this circuitry is used to compensate the inhomogeneity in your magnetic field, either increasing or decreasing. So for instance, if you know by computer, by experimental design that you 100 megahertz, a part of the magnet is 2.299.9911. What you would do? You add 0.1 into it, and if it is more, then you do something to subtract it. So shimming is a process in which you, by using a different circuitry around the probe, you try to make this magnetic field homogeneous for you. So this is your art. This is your art. Remember, as a larger magnet like 1 gigahertz or 1000 megahertz, the shimming become absolute nightmare because the magnet is extremely strong, very, very strong, and the factor in homogeneity are so variable that you have to remember, magnetic power is a vector quantity, so you have to have Z correction, the X correction, the Y correction. You correct the inhomogeneity by a process called shimming, which is a manual process, which is still a manual process, and that's why you need to have a good NMR NMR expert, because without shimming, you cannot record a good NMR spectrum. Okay? Magnet. Anything?
On the other hand, inhomogeneity can also be reduced by reducing the sample size. If the size will be small, then we will need say smaller area for maintaining the strength of the magnet.
Yeah, but the magnet is actually fixed. And the magnet is fixed and the sample volume is required because you need to have a minimum quantity of a sample dissolved in a decent solvent. If you go to a very small volume of a sample, you would have a major problem. Only a part of your sample is experiencing the magnetic field. The rest is not experiencing the magnetic mosaic effect. There's lots of other problems also. So you fill your sample tube to a certain level, or was your level? There is a defined level. There is a circle around your NMR tube, which tells you how much sample you need to have. In order to reduce the volume, you don't reduce the sample size, but you reduce the size of the probe, the tube. So instead of having a 5 mm, you can have a nano probe. You can even have a capillary probe. You can have a micro probe. You can have different probes. But you need to have, for this particular area in which your magnetic field is provided, you must have your sample in this particular area, because you want to make sure that all of your magnetic field is actually applied to the magnetic field. Good. The reason you understand why it's expensive? Look like that I'm selling. Okay. Liquid nitrogen insulate liquid helium from the environment. You can have a very high temperature outside. It's insulated. It just act like a foam around liquid helium. If you don't have a liquid nitrogen, the evaporation rate is very high. Very high, because you see the diver would directly expose to 69 and 25 degrees centigrade room temperature, right? So liquid nitrogen, yes. Lots of different types of metallurgy is used. Different types of alloys are used. So many of them. And the probe technology itself is extremely complex technology. It is not only metal but also thermal coils. Not only metal, but there are lots of thermal coils which keep this probe at God. Oh. Okay. Problem with it. Okay. Yasin, you okay? Okay. So have a seat. Come here. Okay. And इसको बाहर छोड़ दें. I don't want anybody sitting on it again. Okay. Now, having said that, having explained you the technology which is actually involved in superconducting magnet, I want to bring you back to the actual fundamental concepts of spin half nuclei. We all understand that the difference between this energy difference in this energy level is directly proportional to the B. Okay, parallel, anti-parallel, and the absorption takes place when you become a radio frequency, and the condition of in resonance takes place. Now, this is the point I want to leave you. This is the point I want to leave you.
Excuse me? Sorry to cut you off, but I actually wanted to know where the frequency is applied in the instrument. You didn't mention about the frequency, the radio frequency. And
the radio frequency is applied perpendicular to the magnetic field. Frequencies.
Yes, go ahead.
If you want to understand this, you a three-dimensional Cartesian coefficient, right? So the direction of a B naught, and the radio frequency is applied from the XY plane anywhere. And I will tell you why anywhere, because anywhere means a lot. Anywhere means different. So you apply your radio frequency from the XY plane anywhere in the XY plane. is the radio frequency, because the next thing which we will discuss, that how these magnetization vector absorb is depending on the direction of the applied radio frequency. Okay?
Okay, thank you.
I have a question. Like, if you change the direction of the radio frequency, what about the magnitude of that? I mean, if we are providing it 5-degree angle or with the 90-degree
I
angle.
don't want to talk about that. This is coming forth. This we will discuss later, because of a simple reason that it's going to be premature. We need to first understand that. Okay, today, if we have done anything useful, we understood this. We understood that there is a movement of a nuclear spin around its own axis, and when you place them under the magnetic field, there is a precision frequency, and that precision frequency is called Larmor frequency. And when you place them under the magnetic field, this is the one thing which happened, and the other thing is orientation. So you create energy difference between two states, and when you create energy difference, then only radio frequency or any energy can be absorbed. You need to create and then we have also discussed a very simple understanding or of a fact that the energy difference between two energy levels, in case of a spin half nuclei, for example, high energy state and low energy state, is directly proportional to the applied magnetic field. Now, I want to also, in order to remove the confusion, always remember that this is the direction of a magnetic field. So this is the lower energy state, and this is the high energy state. It is different from our own understanding, because we always keep low and high, right? But here is up is because conventionally they have designed, the theory has been designed in a way, and I tell you why it has been designed in a way. Okay, so this is the circular motion, circular path around which this precision takes place. And this is because of a simple physical phenomena called torque. Because remember, torque means when you applied an energy, the species turn them towards a force, towards the force which is applied for. So this is the circular path of precision frequency. And precision frequency, though we already know that it is dependent on the electronic environment, but we need to wait in order to understand why it actually happened, because there is a lots of discussion which we are waiting for. Number two, if I tell you that I don't like this globe, this nuclear, and I just want to use this vector, you should not really be worried about that, isn't it? It's just a vector diagram. So why this globe? Why this circle? Why this dabba? Why this gola? But you don't need to have this, right? You just need this vector, right? And this vector is because magnetic moment is and it has a magnitude and a direction, and this is exactly the same. So if in the future if I don't use this dabba, this circle, please don't mind it, because now I would be going to this particular type of diagram, and I would, with lots of respect, I would give it to the so-called block vectoral diagram, because the name of the person was Eric Bloch. He was the one who first explained NMR by vectors. It's called Eric Bloch vector diagram. Okay, I want to leave you at this stage, and please do not lose this particular momentum which we have generated. And this particular momentum is that now we are going deep into the world of NMR spectroscopy, and we have gone from instrument, we are traveling from outside the instrument to the little nuclei, so-called macro to microscopic picture. This is the microscopic picture of a nuclear species, and that's how things happen. This is the last slide I want to tell you. See, in this case, you have a movement, and you have another movement, right? And this is towards this is precisional orbit. Process is called precision. The frequency is called precision frequency or normal frequency, right? And this is direction of the applied magnetic field. Now, if I want to tell you that if I apply magnetic field from this radio frequency from this direction, this is the answer of your question, that I would like to apply radio frequency at this stage, at this point, from this direction, so-called XY plane. And what this would do, ugly Christmas. Okay. Any question? Yes.
What is the range of your NMR? 300 megahertz NMR spectrum?
The one we have? 300 megahertz. The oldest one, I think, is about 25-year-old. We're still working fine. We have excellent engineers, who can just take it apart and put it back. The most latest NMR we have is about 5 years old, 600 megahertz. Any other question from other places, please? Okay, tomorrow I won't be available. I'm traveling to Islamabad, so my next discussion would be on Wednesday.
Hello.
Yes?
Yes. Sir, I have a question that,
Yes.
sir, how it costs, sir, this NMR, sir. Is it, sir, expensive or cheap, sir?
No, NMR machines are very expensive. I told you there are lots of reasons. NMR quite often now is the most expensive, is the most important and most expensive investment in any laboratory. It's generally in the range of $500,000. Expensive. Any other question?
Ji sir, excuse me. Sir, the direction of the angular momentum, which is in nucleus form, it is aligned with the applied magnetic field having the lower energy state. So, and for the electron, it is a reverse condition. So, is this any conventional mathematical rules or something else?
You see, this is precisely what shielding is. Electrons move in a different direction than proton or nucleus itself. For instance, in this case, spin half nuclei. This is the basic fundamental architect of an atom, that both these charged nuclei, neutron has no charge, but both these charged nuclei spin in a different direction. So that's how the nuclear physics is.
So, sir,
And
why?
This is the reason why shielding takes place, because the electronic cloud generate in a magnetic field which cancel the applied magnetic field.
So sir, why the negative m value for the electron is assumed to be opposed to the field or at low energy level?
No, in all energy levels, it's not low or high. What you are recording option of radio frequency. This property of electrons moving in a different direction than the proton spin is an inherent property of an atom. It has nothing to do with the applied magnetic field. Even without applied magnetic field, they would behave exactly the same, because this is the basic architect of the atom.
Excuse me, sir. Sorry, I could not convey my question exactly. So I mean to say that the energy level of the electron which have the m value is minus half. It is assumed to be it is the lowest energy level, and the plus half is the highest energy level in case of electron.
Not electron. I'm talking about a nucleus spin. I'm not talking about electron at all. Electron comes in the picture when you talk about shielding. I'm talking about the nuclear, plus half and minus half. They are the nuclei. They are the nucleus. And in case of hydrogen, I'm using the word proton, right? But they are nuclear spins. It has nothing to do with the electrons. Electrons comes in the picture when we talk about the electronic environment and the shielding, which we will discuss inshallah. Okay? Okay, thank you very much. Thank you. Allah Hafiz.